All right, the last objective is, since we've looked at so many different types of models, sometimes you might have a couple of ways to re-express or transform a data set, and you have to pick which model is the best. And so that's what this is about. How do we know which relationship or which transformation is the best to use to make predictions? So how is the braking distance for a car related to the amount of tread left on the tires? Researchers collected data on the braking distance measured in car lengths for a car making a panic stop in standing water, along with the tread depth of the tires in 1/32nd inch. Here is a linear regression output for the three different models, along with a residual plot for each model. Model 1 is based on the original data. Model 2 is based, while Model 2 and 3 involve transformations of the original data. So they're comparing the braking distance and, where is it? The braking distance versus the tread depth. And so this first graph, this first model is the original data. This is just what they plotted. And you can see there is an obvious curve in the residual plot, which means that linear model is not a good fit. The second one, they took the natural log of braking distance and the natural log of the tread depth. And here you can see the residual plot. This looks like it's evenly scattered, or there's no obvious pattern to me. And then the third one, they took the natural log of the distance and they did nothing with the tread depth. So here you can see again, there's an obvious curve in the residual plot. So which model does the best job of summarizing the relationship? It's obvious that model 2, because there's no obvious curve in the residual plot. So remember, just using the residual plots to evaluate which linear model is the best fit. So now they want us to use the model to to interpret the residual when the tread depth was 3/32 and the stopping distance was 13.6. So there they gave us the x variable and the y variable for an actual observed data for a car. It had a tread depth of 3/32, and we had a stopping distance of 13.6 car lengths. So first we got to get the equation, which you can see from model 2. Here's your slope. Here is your y-intercept. So that's where y-intercept was, the slope was. And then all you're going to do is you're going to plug in 3 for the tread depth. And the reason it's 3 is because if you look back up here, they tell us that the tread depth of the tires are listed in 1/32 of an inch. So essentially what they're putting is 1 represents 1/32, 2 represents 2/32, 3 represents 3/32. So they're plugging in 3 here to represent the 3/32. So then solving for the predicted braking distance, we end up getting 13.57 car lengths. So the predicted value is 13.57. The actual car length was 13.6. So they're not exactly equal. There's a residual there. And the predicted value was actually shorter than the actual value. So our residual, we do the actual minus the predicted, and we get a residual of 0.03. So when the tread depth was 3/32 of an inch, the car traveled 0.03 car lengths further than the predicted line or predicted model when we're using tread length to predict the braking distance. And so this is the last objective from 12.2. How do you choose which is the best model? And then also a reminder of how to calculate a residual.